On to the chapter called Additional Aspects of Aqueous Equilibria. That really is sort of generic. Basically what it is stuff that didn't fit in chapter 16. Little picky things that didn't fit in chapter 16. Or let's take something we did in chapter 16 and throw some more stuff about it out there. So that's what you're going to see throughout this. The first one is, hey, that ice chart where weak acids break down, let's add to what we're doing. It's not too tough. It's called the common ion effect. Common meaning something in common as in shared rather than common like bunnies are common in my yard. They're there every day. Looking at common being shared rather than ordinary. So what you're looking at is a solution made from a weak acid and its conjugate base. Okay, basically what you're doing is you're going to dissociate the weak acid, like we were doing with your ice charts, and then add more of the anion to change the solubility. If you look at my example, what can I add with formic acid to do this? The correct answer is anything that adds COOH minus. Anything that adds the anion that comes from it, and I picked sodium formate. You'll see an ATE ending on the ions you're going to use pretty often. If you look at Le Chatelier's principle, for my generic reaction of a weak acid, if I added soluble salt Ma, M's a metal, so let's say sodium chloride and my anion were chlorine, if I add A minus, it's going to change my H plus concentration, it's going to shift my equilibrium left, and it's going to increase my concentration of the acid, decreasing concentration of H plus. If I decrease H plus, it increases my pH. It makes it less acidic, aka more basic. So there's your definition of common ion effect, which I think is one of your questions for tomorrow, is very easily to write that down. Put it in your own words. Think about that. Let's do the practice. So we've got the concentration of H plus in a solution containing both 0.50 molar HF. So let's look. Okay. And here's where your common ion comes in. 0.10 molar NaF, sodium fluoride. What's its pH? You need two equations. Technically, you don't have to write the one on the left. If you realize that sodium fluoride is a strong electrolyte and is going to break down to give Na plus and F minus, you can do that one in your head because you realize NaF just means that I have some fluoride ion, hanging out in solution. Do I have any H plus? Not yet. Not before everything breaks down. So my concentration might change. Well, I'm going to have to make that side because I have no hydrogen and I need a pH. So I'm going to lose the concentration of HF. I'm going to gain some hydrogen and gain some fluorine. So 0.50 minus X molar, X molar, and 0.10 plus X molar. Do I really think I'm going to need to keep the X's? Because this looks like a mess. So what you can see here is where the common ion came in and where it made that mess. All this is an ice chart with some fluoride ion starting. Yeah, I figured it out there, and we are indeed ignoring X. So I'm going to write my Ka expression, just like always. It does not involve that dissociation of sodium fluoride. It's just still going to be H plus, F minus, HF. We already figured out that we can ignore X, so I'm just going to talk from your packet now. We've got this all set up, and I would substitute in my values. 6.8 times 10 to the negative fourth, 0.10x over 0.50. Pretty easy to solve and get my concentration of the hydrogen ion, and then to calculate pH from H, giving me a pH of 2.47 as negative log. Not too bad. You know what? We've got time. Let's do part A of question 15 so you can get a little more practice in picking out what we're looking for. At very least, I'll set that up for you. You know what? I don't think Well, yeah, I'm going to be writing a lot longer things. But what you're going to see in general, and this might be the height of laziness, but what you're going to see in general is a really similar structure with common ion effect. You're going to see no hydrogen. You're, for our purposes, usually going to see a monoprotic acid, only giving up one proton. So you'll have H plus something. You're going to have some acid breaking down. I'm going to read 0.060 molar in potassium propionate. And 0.085 molar in, there we go, propionic acid. I go for the name of the acid first. HC3, looks like H5O2. And I would be willing to bet then that the propionate ion is just take off that hydrogen, C3H5O2, and that minus even stayed where I put it. There we go. Once I did that, I can do the rest from here. 0.060 molar potassium propionate, and I'm starting off 0.085 molar in propionic acid. And I've got my Ka value there. If I want to write my Ka ahead of time, I definitely can. It's always going to be H plus and my ion, my anion, and then combine the two for my acid on the bottom. We'll solve for that. I'm probably just going to write it, might even just erase. Who knows? 0.085 molar, or sorry, 0.085 technically minus X molar. We got to think that through at least. X molar. And 0.060 plus X molar. Now, I did this ahead of time. I did check. When I divide, I get something based on my pH, or sorry, my Ka. I do get an X that I can ignore, because when I divided that little number, which is already tiny, by a really, really tiny number, 10 to the negative fifth, I got some thousands. So I'm able to ignore X. So there it goes. What I'm going to end up with here for my concentration of H is X. For my propionate, 0.060. And for my propionic acid, 0.085, equal to the Ka I gave you. When I went to do this, I did not have a Ka value. I was using the book, and I was sad. So there we go. There's my Ka. Pretty easy to solve for X. There's no squareds. There's no anything. 1.3 times 10 to the negative fifth times 0.085 equals, divided by 0.06 gave me X equals 1.8 times 10 to the negative fifth. And that's going to be my concentration of hydrogen. Sometimes you'll get an assignment to calculate the pH before or without the common ion, which you would just take that out without the common ion, and you would get a chance to not ignore X, calculate your pH like we did last chapter, and you'd look at the changes. I'm not sure if any of your questions coming up in your chapter have that, but this one does not. To get the pH of this, negative log that. Work through this on your own. I got a pH of 4.74 for this one with the common ion present. So there's an extra bonus example. You've still got parts B and C. You'll need KB for part B and Ka for part C, which I've given you. That's common ion. Have a good day.